Hey guys, welcome back. It is April 14th, another edition here of Kitchen Table Chemistry. Today, what we're going to look at is the ability to determine the concentration or time to concentration of a first order reaction. This is kinetics again, and this is about what it happens to concentration over time. Now, these are called integrated rate laws. We'll look at them separately as first order and then second order, and then a little bit about zero and other things past second order. So integrated rate laws, in a first order reaction, the linear relationship is the natural log of A, ln of A, and just so that we remember, ln is the natural log. And you get a linear relationship when you compare that natural log to time. Ln, again, natural log. And we're going to see a little bit of lowercase e here, which is a base of the natural log. We're going to be using K, which is the constant, and we've seen that before. That is the constant for the reaction. Because these are all first order, K will always be seconds to the minus 1. And then time will be seconds or minutes, depends on what we're looking at, but it'll always be a unit of time we understand. The natural log of concentration against time gives us this nice linear relationship. So that will let us determine concentration change over time. And the idea here is that we know once a reaction gets started, we know after a period of time what that concentration is. So these are the formulas. Ln of A at time over A at 0 is equal to negative KT. Ln of concentration of A at time. So this is whatever time we're looking at. And A at 0 is the initial concentration. So the start concentration. Negative K T. So Ln of the concentration at whatever time we're concerned with over the initial concentration is equal to negative KT. Or concentration at time, if that's what we're trying to determine, is equal to the initial concentration base natural log negative KT. Both of these are essential. Make sure you've got them copied down and make sure they're copied down correctly because they will be with us for the rest of the unit. Half-life looks like this. The half-life is equal to ln of 2. Natural log of 2 is always the natural log of 2, which, by the way, is 0.693, a number that you end up memorizing, over K. So if you know K, you can figure out the half-life, and if you know the half-life, you can figure out K as well. That's the neat part about first-order kinetics like this, is that you can always find K if you have the half-life. All right, what do these things look like? Here's a situation. How long would it take for a sample of sucrose to decrease down to 20% of its initial concentration? And then it gives us the rate constant is 6.17 times 10 to the negative 4 per second. So K here is 6.17 times 10 to the negative 4th per second. Time is the X that we're trying to find here. We're looking, how long does it take to get down to 20%? And at time 0, we had 100% of whatever sample size. So even though I don't have the sample concentration here, many times we can just work in percents like this. So now what I have is this. I have the ln on the top, the concentration, and I'm just going to sub in the letter A for the sucrose here. Ln of A at time over A at 0, large, there we go, is equal to negative K times T. So ln, and that is going to be 20% over 100% is equal to negative 6.17 times 10 to the negative 4 per second times time, which is the unknown. I then take the ln of 0.2, so what I get then is negative 1.609 is equal to negative 6.17 times 10 to the negative 4 times time. I'm then going to divide that by, so negative 1.609, run out of space here, divided by 6.17 times 10 to the negative 4. Seconds now creeps up to the top over time, and I get a time value for this equal to 2,608 seconds. So that is how long it takes to go down to 20% of its initial concentration. That's how we're going to solve these. Okay, here is a second example. It's a first order reaction, same thing with sucrose here, and calculate the half-life. So to get the half-life, we're simply going to take the ln of 2, natural log of 2, get used to doing it on your calculator, it's 0.693, divided by k, which is 6.17 times 10 to the negative 4. Now, seconds reciprocal is the unit, so seconds ends up at the top, and that'll end up being our only unit there. So the half-life here ends up, we just have to divide those two numbers, and I got 1123 seconds as my half-life. So that is the half-life of sucrose from this example. That's how we do this. Now, I provided a few examples for you to take a look at. Take a look at them. Send me your answers. I'm interested in seeing how you're doing and how comfortable you are with this. I thought that we would practice this Thursday and Friday this week, looking at different ways of doing it. I also thought tomorrow we could take a quiz, and that this will be our first online quiz on rate laws, which was what we were working on last week. So that quiz will come at you tomorrow morning, and you'll have the entire day to go at it. If you've got stuff going on tomorrow and you know it's going to be an issue for doing the quiz, just shoot me an email and let me know that you don't have a block of time where you can do that, and we can work around that. I look forward to seeing your results from this, your quizzes on Wednesday, and then I will return with another video like this on Thursday. Take care, guys. I hope you're doing well. Bye-bye.